All right, Aaron, we almost forgot about you, but never fear. We're going to go back over some of what Meredith and I just talked about, and explain the difference between the binomial PDF function on the calculator and the binomial CDF function. The PDF stands for probability distribution function, or you'll sometimes hear that called probability density function, and that's going to calculate binomial probabilities for you for a specific value of k. So the example that we have here, if you are looking at an experiment where you have 20 trials, binomial distribution or binomial probability, so we're running Bernoulli trials. Let's say we have 20 of those, and the probability of success on any one is 0.5, and then we want to know the probability that we get exactly 5 successes. We've got this formula down here that we developed in class on Monday, and we could use that to do the formula, to compute the probability, or we can use this binomial PDF function that we also talked about on Monday. But if we wanted to know something like, instead of exactly 5 successes, suppose we want to know the probability of 0 through 5, in other words, at most 5 successes. So if we wanted to do that, we could use the binomial CDF function on the calculator, and the C stands for cumulative, so binomial cumulative distribution function. And in that case, we'd still put in the parameter of n, which is the total number of trials, p is the probability of success on any given trial, and k is the upper limit. So we're looking at the probability of 0 through k successes. And we're going to do some examples here from the textbook. So Meredith and I are starting out with example 5, which is at the bottom of page 488. So you might want to flip to that in your book and follow along as we talk about it. And Meredith's going to be kind enough, if she will, to read that example. And then we'll look at how we would use the binomial probability formula to solve it, and then how we would use the functions on the calculator to solve it. Okay, take it away, Meredith.
Example 5.
Yes.
A machine produces light bulbs to meet certain specifications, and 80% of the bulbs produced meet these specifications. A sample of 6 bulbs is taken from the machine's production and placed in a box. What is the probability that at least 3 of them fail to meet the specifications?
All right. So what's the probability that any any bulb chosen at random fails to meet the specifications?
1/5.
Okay, because we know that the probability that they'll pass, that they do meet the specifications, is 0.8, and so the probability that any given one doesn't pass, doesn't meet the specs, is 0.2. So that's what we're going to use. It's a little awkward in this case because we're used to talking about the probability, about P as being the probability of success. But in this case, because we're looking for the probability of failure, P is actually going to represent the probability that a given bulb fails. In other words, failure is success in this example, which is a little bit backward. We could certainly switch up P and Q if we wanted to, but I think it might actually be easier just to stick with the same terms that we have been. So we'll let our value of P equal 0.2, and we want to know, if we're going to grab 6 bulbs out of this batch, what's the probability that at least 3 of them fail to meet the specification. So either 3 will fail, or 4 will, or 5 will, or 6 will, out of the 6 that are chosen. So Meredith, what are we going to use for n in this example?
6.
Right, because there's 6 total. And our value for k, let's talk about how we would do that. We want to know the probability of 3 failing, or 4 failing, or 5 failing, or 6 failing.
4.
Okay, and what will that give us? And which formula will we use, or which calculator function? Will we use the binomial PDF or binomial CDF?
CDF.
And what value for K?
We don't have to use 4.
So you want,
Or you could use 6 and then minus.
all right, let's talk about that. Let's scroll down a little bit more. Whoops, I think it's probably on the calculator, just BINOM. It stands for binomial. So the number of trials in this case is 6, because we're choosing 6 bulbs in all. And you can just think of drawing out one of those at a time, or selecting one of those at a time. And the probability that an individual one is going to fail is 0.2. And we want to know the probability that 4 fail, or 5 fail, or 6 fail. Actually, I think it might have been even lower than that. Was it 3? At least 3. So 3, or 4, or 5, or 6. If we use the binomial PDF, we could add up the probability that 3 fail, plus the probability that 4 fail, or 5 fail, or 6 fail. What would be a shorter way of doing that with binomial PDF than adding together all 4 of these probabilities?
Use the CDF.
Okay, yeah, we could use CDF instead of PDF. All right, so if we use CDF, let's say you were wanting to put in 4 here. If we put in 4, that's going to calculate the probability that 0 fail, or 1, or 2, or 3. And it'll add those together. Let me fix that cable. So it's making this change colors. All right. So this won't actually give us what we want. Actually, this one won't. It'll also be or 4 and add those together. So it goes 0 through 4 probabilities, but we want 3 through 6.
So you don't have to do 6. You would put or CDF 6, and then you have to subtract 2.
Binomial CDF of 2? Okay. What is a binomial CDF of 6? Let's actually try that on the calculator. So 6, comma, 0.2, comma 6. Yeah, that's under distribution, second distribution, and then we'll arrow down option B, I think. Whoa, how is it working? Okay, let me just get out of this and try again. Oh, great, the whole calculator's locked up. I think maybe I pressed the buttons a little too fast. What did you get, Meredith, when you put in binomial CDF 6, comma, 0.5, comma 6?
I got 1.
You got 1. How's that possible?
Well, I guess it makes sense.
Why is that?
Because, like, probability that all of them are.
Yeah, it covers all the possibilities. So either there were 0 failures, or there was 1 failure, or there were 2, or there were 3, or there were 4, or there were 5, or there were 6. So that's 1. So it's true that we could use the binomial CDF function and do 6, comma, 0.2, comma 6, but we know that's equal to 1 because it covers all the possibilities. So we could just take 1 minus the binomial CDF 6, comma, 0.2, comma 2. And that's equivalent to what you initially suggested, but it'll save us a little bit of work because we already know the value of 6, binomial CDF is 6, comma, 0.2, comma 6. All right, let's see if I can do this again without angering the calculator. I'll arrow down nice and slowly. There we go. 9. So there's about a 10% chance that 3 or more of these will fail. Now let's talk about whether that makes sense or not. By the way, you can see that exactly matches the answer in your book. What a coincidence. 10989. And it took them a whole lot more work because we used the CDF function to save us some time. And they may have, no, they never did go back and use binomial CDF. Strange, they just introduced it on the previous page but then chose not to use it. Okay, well, who knows? Anyway, any questions? Does that make sense how we did that? I'm going to fix this. All right, let's talk about whether that answer is reasonable or not. So the probability of choosing, and you reach in, you pull a bulb out at random, the probability that it's a bad one is about 20%. Does it make sense to you then that the probability of getting at least 3 bad ones, if you choose 6, so in other words, at least half of them being bad is fairly low. Probability of the bad one on any draw is 20%. So you go and you take out 6. Probability that you get at least half of them being bad. You really probably wouldn't expect that, would you? Probability is 20%, I believe.
Well, if you take 0.2 times 0.2 times 0.2, you only get like 1%. So okay, that made no sense. Okay, I thought we got the answer. Okay, sorry, never mind. I mean, yeah, I guess that is kind of, because you would expect for it always to be like one of them.
Okay.
Because only 20% from the beginning. Yeah, that doesn't really make sense.
Yeah, if only 20% are bad, then it's not very likely that at least half of the ones you pull out, you pull out 6 and you're going to get at least 3 bad ones. That's not very likely. So, while you might not say, oh, yes, I would expect that probability to be approximately 9.9%. You might not get that close, but you can say, yeah, it's not very likely, so that's a reasonable answer. All right, let's look at example 6. A little wine tasting here. So we've got someone who claims to be able to distinguish between 2 kinds of wine with 90% accuracy.
Pardon the interruption, but Mary Beth and Emily Webb, please go to the front office. Mary Beth and Emily to the front office.
And so he's applying for a job, I think, as maybe a sommelier or a wine taster. And let's see, he's going to taste the 2 kinds of wine 9 times and take a break after each one to clear his palate. And it's agreed that if he's correct at least 6 out of 9 times, he'll be hired. And so the first question is, what's the probability that he'll pass if he's just guessing? In other words, he's really not who he claims to be. He really can't, with 90% accuracy, determine between 2 types of wine and identify them. So if he's really an imposter and he's just guessing, what's the probability that he is successful on any one guess?
Oh.
He's got 2 bottles there.
Yeah. So like 1/2.
Yeah, his probability of success is 1/2 per guess. If he's truly just guessing and really doesn't know the difference between the wines, be like me trying to test these. Probability 1/2. All right, so we want to know what's the probability that he will pass and be hired if he's just guessing. And you might remember that we set up here, he's going to pass and be hired if he's correct at least 6 out of 9 times. 6 out of 9. So we want to know what's the probability that he's correct 6 times, or 7, or 8, or 9. 6 or 9 times. This arrow is not really standard terminology, but I like it, so I'm using it. All right, so how do we get this probability of 6 through 9 correct answers? We know the individual probability is 0.5, if he's just guessing.
So,
The number of trials is 9.
1 minus the binomial CDF, let's use 9, 0.5, 4, no, 5.
Very good. It's absolutely right. 1 minus binomial CDF, parentheses down here, 9. The 9 trials, 0.5, probability of success on any individual one, and we only want to go up through 5, because we want to calculate the probability of 0 through 5 successes, and then we'll subtract that from 1, and that'll give us the probability we really wanted here, 6 through 9. All right, what'd you get?
I got 5.
All right, so if he's just guessing, there's still about a 25% chance that he'll be able to successfully, pass himself off as a connoisseur, a line expert. My guess is they probably figure out soon enough that he's an imposter, but who knows? All right, second part of the question here. What's the probability that he'll pass if his claim of being able to distinguish the lines with 90% accuracy is correct? How does that change the way we do this? If he's telling the truth, he really is 90% accurate.
Then your value for P goes up to 0.9.
Right. So let's just change this to 0.9. What'd you get?
99 for 99%.
All right, so if he's legit, he's going to pass. There's a very, very slim possibility that he won't pass if he's legit. Did you say 99.2?
Yeah, sorry.
Just look at the answer report. All right, does that make sense?
It's so
Yes, we are.
oh, I didn't know it was a little again.
Yeah, I just minimized it, but it is still recording. Let's see, I do want to give you resource time today, but I want to look at one more example here. Let's look at example 8 on page 491. This is about error correcting codes. Unfortunately, when an electronic message is being transmitted, it's possible that sometimes it doesn't get transmitted exactly correctly. And so in order to minimize the chance of error, we have these procedures called error correcting codes. And one of these is the Hamming code. And they talk about this a little bit in what's leading up to this example. But we're not going to spend a lot of time going through that. If you're intensely interested, there's plenty there you can read about that. But suffice it to say, the purpose is to minimize the likelihood of an error when you're transmitting an electronic message. And that data might be, sending a message from here to outer space, or it might be transmitting your PIN when you're logging into your banking account from home. Something, any kind of electronic transfer. You want to minimize the likelihood that there's an error in the transmission. And so we have a really simple example here. I've got a message consisting of 7 symbols, and the probability that that any individual character in that message gets transmitted correctly is 0.98. So this is pretty good transmission. And so first question is, what's the probability that the message is received without any alteration? In other words, all 7 characters are transmitted correctly. Well, it's 0.98 for any individual character, but we want to know what's the probability that all 7 are transmitted correctly.
87.
All right, and how'd you get that?
0.9827.
Okay, and that's consistent with the formula that we had up here, because if you look at this formula, we've got 7 choose 7 here because there are 7 characters altogether. We want to know what's the probability of 7 getting transmitted correctly. Excuse me, so 7 choose 7 gives us 1 here, and then probability of success on any one is 0.98. We want 7 successes. Probability of failure is 0.02. We want 0 failures, so this would be this is just going to give us 1 over here because 7 minus 7 gives us 0 for our exponent. So 0.02 to the 0 power. So then we can figure out that plus 1. And then times 1 over here. So there's your 0.98 to the 7. You might not have thought about it that way, but I want you to see that it's consistent. Your thinking is consistent with this formula. All right, so about 86% of the time the message will be transmitted correctly. Now, using this Hamming code process, the message will be received correctly, if we'll go on the next page correctly, even if one symbol is changed. In other words, it's capable of correcting up to 1 error in the transmission. And so we want to know now what's the probability that the message is received correctly. But in this case, we've got a little bit of leeway because it gets received correctly if either 6 characters are transmitted correctly, or 7. 7 characters are transmitted correctly. So we have to consider 2 cases here. We need to know the probability that 6 characters are transmitted correctly, plus the probability that 7 are transmitted correctly. And we retain our probability of success on any individual character being transmitted correctly. That's still at 0.98. So 0.98 probability of success. 7 is our value for n. And then we want to know the probability k equals 6 or 7. What'd you get?
I got 1 or 10%. That was not right. Could I use a PDF? I just did the
Binomial PDF of
Six.
what? 6?
6 and then plus 7.
Plus binomial PDF of 7? Yeah, that should work. Let's try it again here. Is that thing good? Is that option B for CDF?
CDF is B. PDF.
We use PDF. Yes. And I can't read the letters. Here it is. Alright, so we take binomial PDF of 7.
Oh, that's what it was. I thought 9, not 7.
to. And you can see that makes a big difference, that I think this error code can, or this process can self-correct one character. We go from about an 87% successful rate of transmission to 99%. That helps a lot. And some can correct more than that, and that's what example 9 is about, but I think you get the idea. All right, what would have been an alternate method for doing that? This is correct, it's fine, but what's another method for doing it? Save us a little bit of time.
The binomial CDF, or I guess 1 minus the binomial CDF of 7, 0.98, is it 5?
It is, yeah, because 1 minus the probability that the probability of 0 through 5 characters being transmitted correctly. So that leaves you with probability of 6 or 7. So yes, that should give you exactly the same answer. All right, so I have some practice for you, which you can either work on now or you can use this remaining time as your resource. It's up to you. This is and you can see here, I'd like for you, for at least half of these, I want you to write out the formula. So, you know, if I were you, I'd pick the ones that have only one part to write out the formula, and the ones that have multiple parts, use the calculator. But I do want you to know that formula and see how that's actually consistent with what we've already been doing. We've already been calculating binomial probabilities, we just didn't call them that earlier in the book. Some of these questions ask you to draw a tree diagram, and that helps you see the connections even better, I think, between this section and what we've done in the past. All right, these are pretty straightforward. They're all odd, so you can check all of your answers with the book. You have a good idea whether they're correct or not by the time you come in tomorrow. So we will go over these tomorrow in class and probably get into the next section, which is on expected value. I would really like to be able to finish this chapter and have a little assessment next week before spring break. But we'll see whether that's realistic or not. We've got a couple more sections to do. And on Thursday, I think we're taking a survey that'll take up most of class, so we don't really have Thursday, so we got
Surveys are what?
youth risk behavior survey that all the Catholic schools are taking. So it's a fairly lengthy survey, 85 questions or something like that. So we're doing that in math classes. But it should be painless enough. I'm going to ask you all to bring your devices in and just use those to take it. It'll all be online. All right, so that's where we are. Aaron, we're signing off now. We certainly hope you've enjoyed this visit to class without being in class. Let's see if I can find out how to turn this off.